using this conceptual understanding, let's start to develop, again, like an approximate conceptual model of how thermal boundary layer and momentum boundary layer do grow. And then we can use that to start estimating things like the heat transfer coefficient and shear stress, which ultimately are things that we care about. Okay, so the question, how do thermal waves grow as a function of position or time? So let's go back to this idea where we said for a semi-infinite problem, conduction problem, we said that the thermal depth, delta T, is approximately equal to 2 times the square root of alpha times T, right? So why am I, by the way, introducing this idea of a semi-infinite conduction problem? Well, I said that this is laminar flow, so there is no momentum transport in the y direction. The only way that heat can move in y is by conduction. So in effect, this is a conduction problem. Like, convection is a conduction problem. It's just that we have to use this like conceptual model where it's sort of a transient response in 1D in conduction in the y direction. So let's use this idea of delta T is approximately equal to this, and let's adapt it for this situation. So let's say, what am I going to use for time here? We have a spatial problem. This is a steady state problem. But what am I going to use for time? I would say I want to know how long the fluid at any position has been in contact with the surface. That's my measure of time. So I can estimate that by saying T is equal to my position x over the free stream velocity. Right, so I have position meters over meters per second, so that becomes seconds. That's an estimate of the amount of time at a given position I'm in contact with the surface. So knowing that, I can go and substitute that in here, and that's going to become delta T is approximately equal to 2 square root alpha x over u infinity. All right. So the first thing we can notice is how does the boundary layer grow as a function of position x? Well, it grows like the square root of x, which is what we saw when I drew it, right? That looks like this, right? It's this sort of initial growth, and then it slows down. So we're growing like the square root of x. This is my exposition. So the same thing, right? This is how the thermal boundary layer grows. The same thing, same kind of ideas can apply for the momentum boundary layer. There we're going to say delta sub m is approximately equal to 2 square root of something times my normalized time there. What is the thing that is, if alpha is the thing that's transporting heat, my thermal diffusivity in a thermal problem, what is the thing that's transporting momentum in a momentum problem? Yeah, yes. Right? Viscosity. So that's going to be, I'll use nu, right? So that's my kinematic viscosity. Nu times x over u infinity. Right? So, by the way, nu is kinematic viscosity, which is defined as mu over rho, and that has units of meters squared per second. So as a diffusion, right, a diffusive property, it makes sense that you're looking at how much area is it affecting per second, right? That the units kind of make sense there. So okay, this is going to be how your momentum boundary layer grows. What else can we say here? So you could do the same thing for other things, like if you had some problem involving chemical species and you want to know how's my ion concentration, how is it diffusing as a function of time? It's going to follow the same thing. Anytime you have a process that's governed by diffusion, these are diffusive processes, it's going to be governed in the same way, approximately. Yeah. Yeah, so if you remember back to the 1D transient problem, we said if I want to estimate the depth of conduction into some wall, right? How long does it take, or like at what time At a given time, how far have I conducted? I say that right. At some time, how far have I conducted, right? That was the approximate relationship we came up with. And that was what we used to develop the diffusive time constant as well, right? That tau diff is equal to L squared over 4 alpha. Okay? So let's see. So let's clear up a couple things here. I just want to make a few notes so we have these down. So alpha is essentially our ability to transport energy by conduction, where the kinematic viscosity is the ability to transport momentum. All right. So one other concept that we can now define here, this is going to show up in all of the convection stuff that we're using, is the idea of a Prandtl number. So Prandtl number is a non-dimensional parameter, and it is an indication of the ratio of these two things. So Prandtl number tells us, just by its definition, we have nu over alpha. So that's conceptually just momentum over energy, or thermal energy, right? Diffusion of momentum over diffusion of thermal energy. If you look at the stuff that's involved here, right, in both alpha, which is K, conductivity over density times specific heat, and kinematic viscosity, which is dynamic viscosity over density, those are all properties of the material, right? Nothing in this depends at all on the flow or the application. It's entirely properties of the material. So for a given fluid, I guess at a temperature, maybe at a pressure, you're going to be able to compute what the Prandtl number is, and that's not going to change, right? So the ability of a fluid to transport momentum over the ability to transport energy is captured this way. I'll say, just as rules of thumb, most fluids have a Prandtl number approximately equal to 1. And it turns out, I guess, that the reason why that is the case is the mechanisms that affect momentum transport are really similar to the mechanisms that affect energy transport. Right? You have, in order to transport momentum, you need individual particles in the fluid sort of interacting with each other. And that type of process is going to be replicated in both of these situations. If you have, let's say, a fluid where you have a lot of free electrons, like it's a liquid metal or something like that, then you're going to have a Prandtl number that is not at all close to 1. So let's see, examples would be, right, air. Air is Prandtl number of about 0.7. Liquid metal, Prandtl number is usually much less than 1, right? Because it doesn't transport momentum very well, but it really transports energy very well. Another sort of opposite end of the spectrum would be oils. Those are going to have a Prandtl number of much greater than 1. So like your engine oil type thing. All right. One other thing that we can do now is we've introduced the idea of a Prandtl number. That's just a property of the fluid. We also want to introduce, I think you've already been familiar with this, but the idea of Reynolds number. So Reynolds number is, again, a non-dimensional parameter, and it is defined generally as density times some characteristic velocity times some characteristic length divided by viscosity. So we are here looking at the ratio of the momentum of the fluid to the viscosity or shear stress forces in the fluid. So if you have like a flow that has really high velocity, the momentum part of that's going to be really high relative to the shear stress part of that. Okay, so that's your Reynolds number. I think you've seen that before. By the way, let me just write out one more thing here. So for external flow, we're going to say Reynolds number is equal to density times what's my characteristic velocity for flow over a flat plate? That's going to be u infinity. Times characteristic position is going to be x over mu. Sorry, I made this kind of tight. So for every problem that we're going to deal with in convection, you have to be really careful. It's sort of like the fin conduction problems and things like that, where you have to be really careful about what these characteristic things are. The formula itself is really simple. What is my characteristic velocity? What's my characteristic length? For a flat plate, it's going to be how far I've traversed along the plate. That's the thing that really affects the Reynolds number. For other stuff, flow over external extrusion or internal flow, it's a different characteristic lengths. Okay, questions on this stuff before we move on? Okay. All right, so let's, with these definitions in mind, what we want to do now is get to a point where we can use our approximate understanding, or using this like approximate diffusion model, to compare it to the known like exact solutions for these types of problems. So let's go through this. Let me just write out first what the exact solution is. So if I wanted to know the momentum boundary layer thickness, the equation for that, which is derived using a self-similar solution, which is sort of this implicit solution. We're not going to go through that, but you can kind of look in the textbook for it. So that's going to be delta M is equal to 4.91 times x over the square root of the Reynolds number. So how do we get to something like this using our conceptual model, which is shown above? Let's just go through a few steps and you'll kind of see how this plays out. So the first thing we want to do is let's take our delta M, the equation on the top, and divide both sides by x. So delta M over x, 2 over x, square root of nu times x over u infinity. And then using that, let's simplify the right-hand side. Let's bring that x inside the square root. And that would become the following. It is delta M over x is approximately equal to 2 square root of nu over, now x is in the denominator, times u infinity. All right, so this, if you look at it, is sort of like the square root of the Reynolds number, right? Or 1 over the square root of the Reynolds number on the right-hand side. Because you have your kinematic viscosity, which is mu over rho. So that is actually the Reynolds number inside there. So this simplifies further to delta M is approximately equal to 2 times x over square root of Reynolds number. All right, so just simple math there and a few substitutions. So we now compared that to the known exact solution. So it, in form, looks really similar. But the difference is that the known exact solution is saying, actually, the rate of growth is about 2.5 times what your approximate model is going to tell you. Like, what is the difference there? Why is it different? I mean, first of all, it's good that it's the right order of magnitude. That's sort of a good sign. But why is it different? Well, I guess one thing, this conceptual model is assuming conduction in a sort of fixed plane, right? Here we have fluid that's like sliding over itself. So as you go further out, you get the fluid that's sort of being replaced by slightly cooler fluid to the left of it, right? As we drew this sketch. So there's this like additional gradient or an additional like temperature difference that accelerates heat transfer. Right? So that's like one small part of it. The other part of it is that this definition just happens to use a slightly different threshold for what the boundary layer is. So it's a higher number than 99%. But okay, so conceptually you can understand where this model came from, right? We can do the same thing for the thermal boundary layer. Thermal boundary layer is going to be, let's see, we start with this, And we wanted to end up with what's our known solution. So the known solution is delta t is equal to 4.91 times x over Reynolds to the 0.5 times Prandtl to the 0.33, or to the 1/3 power. So we want to take this thing and get it to look like this. We'll do a similar process. The similar process is going to take, we're going to divide both sides by x and bring that x inside. And so we end up with delta t over x is approximately equal to 2 times the square root of alpha over x times u infinity. Right? Alpha is k over rho c. So what do we do with that? So we need to introduce the viscosity in some way if we wanted to get the Reynolds number in there. So let's introduce the viscosity by, I'll just draw it like this. So within the square root, let's multiply by nu over nu. Okay, and then we can use that definition to simplify down to delta t over x is approximately equal to 2 over the square root of Reynolds number times the Prandtl number. All right, so just remember, I guess you could go through it yourself, but nu is mu over rho. So mu over rho, rho over mu. And so you have this like Reynolds number term, and then you have a Prandtl number term that pops out of that. So you're left with both of those things. So the only like difference here, by the way, is this thermal boundary layer. It's the same formulation as that, but it's saying that there's an additional rate of growth, or a change in the rate of growth that's proportional to 1 over the square root of the Prandtl number, which makes sense, right? Because the Prandtl number tells you the relationship between momentum and thermal boundary layer growth. Okay, so with that, we can compare to what we have down here. And I guess you see it does look, again, really similar. You have this 4.91. We have square root of Reynolds number, and then we have Prandtl number to the 3rd power instead of the half. So it's conceptually, very similar. One thing we can do with this is we can take these two boundary layers, so delta m over delta t, and I want to compare their rate of growth, right? The ratios of the rate of growth. So if we do that, let's just plug in the formula that we came up with here. So that would be 2x over square root of Reynolds times 1 over 2x, and the numerator would be Reynolds times Prandtl. So that's just taking the approximate models for both of those. And if you look at this, right, what happens? So the x's cancel out, square root of Reynolds cancels out, and you end up with this ratio being square root of the Prandtl number. So this is telling me that if I want to know how fast the boundary layers grow, it is given to me by a fluid property, right? And it's the square root of the Prandtl number, or the Prandtl number and then square these, right? That's going to give you a relationship. So it's kind of an interesting observation that you can you just predict based on a property of the fluid. Okay, all makes sense. Any questions on that? Okay, so let's try to use top hat now.
Can we get the
Oh,
same,
go ahead.
approximation if we use the implicit real solutions, but it would just be Prandtl to the 3rd power?
Yeah, I guess you would.
Okay.
Yeah. So I mean, these are all these are all conceptual models, and when you're talking about, I should say this, right? When we're talking about convection correlations, there's often a lot of uncertainty associated with these. So you can go through and you can get an order of magnitude answer for this type of a problem. If you go and actually measure the heat loss over your device in a condition, if you got within 20% of your correlation, you'd be really happy, right? That's great. Normally what you would see is, for any experimental work, you're like order of magnitude, that's kind of what you're looking at. Really what you're going to need to do for a lot of real applications is go to correlations, and correlations are going to have more accurate estimates, but there's still this margin of error on those. So when people say, you know, if you can quibble over the 0.33 or 0.5 exponent, I mean, you're sort of like arguing about stuff that is noise in the problem. So the question is, which conceptual model most closely resembles convective heat transfer in a laminar boundary layer model? So what we've been talking about, which of these is going to be kind of the right analog for this type of problem? Okay, let's see what you said. So responses. All right, so we have, okay, works, this is nice. D, okay, 1D transient conduction in a semi-infinite domain. So that is the right answer. 1D steady state conduction, 2D. So the reason why A is not the right answer is because we're thinking about how heat is transferring in sort of a piece of fluid that's moving along the plate. So although once you come up with a model for it, it is a steady state model, the right analog is looking at how heat sort of affects a slice as it's moving across the plate in time, right? So when we go through and we substitute that x over u infinity, that sort of takes time out of the equation. But the right analog or the right conceptual model ends up being the 1D transient model. So 2D steady state conduction is not right because we're just looking at one sort of, we're looking at conduction in one coordinate.